Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of a series of videos as an introduction to limits in Calc 1 or differential calculus. We have just discussed the basic non-rigorous definition of a finite limit at a finite point. We didn't really have a ton of examples. Most of them in this series are going to be more computational, using tables and graphs, but we'll eventually get into the hardcore definition. But before we do, let's go ahead and talk about single-sided limits. So the left-hand limit, or the left-hand single-sided limit, it's this notation right here. You would read it like we did before. In this case, we're going to say that this notation means the limit as x approaches a from the left. That's what this minus sign here means. You're from the left-hand side of a, or what we call below a. So the limit as x approaches a from the left or from below of f of x is L. Now, visually, what does this look like? Oh, and I should read the rest of the definition, by the way. This means that we can take the values of our function arbitrarily close to L by letting x be sufficiently close to a as long as x is less than a. So visually, and let me get my ruler out for this, visually, this looks like the following. Let's suppose that this is our function. It's a piecewise defined function. It exists at a height of, I don't really care what this height is, honestly, but let's go ahead and just draw on a y-axis here. And let's say that that height is 5. And let's pretend that this height right here is 10, just because it looks like it should be. And on the x-axis, let's pretend that this x value that aligns right there is 3. Then what we can say about the limit as x approaches 3 from the left of this function, it looks to be 5. As x gets really, really close to 3, these y values get really, really close to a height of 5. So this would be the single-sided limit, or the left-hand side limit of that curve. Now, let me just tell you, the fact that the function's value at 3 is 5 does not matter. And in fact, that could have been an open circle right there. The reality is, when you're working with limits, x is not needed to be 3, or in this case, 3. It doesn't need to actually be 3 or a in the definition case. It doesn't need to be a. X is never going to become a when you're working with a limit. It's just going to get close to that. So our x values are going to get really close to 3, never touching 3. So as long as we allow our x values to get super close to 3, but from the left-hand side, our y values are approaching 5. Now this limit is one of my favorite limits. It's a really, really fun limit. Let's go ahead and evaluate this limit, the left-hand limit, as x gets really close to 0 from the left-hand side, and see what happens. We're going to go to Desmos and build a table of values. So we're here over in Desmos, and I've already written the function in, f of x equals sine of x over x. The one thing I don't want to do is spoil the surprise by graphing this function. I want to showcase, using a table, the left-hand limit as x approaches 0. Just remember, sine functions, or I should say trig functions, are automatically considered to be in radian mode when you use the graphing calculator in Desmos, and that's exactly what you want in calculus. You want to be in radian mode. So let's go ahead and add a table here, and let's change the y values of that table to be f of x sub 1. Now we want our x values to approach 0 from the left-hand side. This is a single-sided limit we're concerned with. So let's go ahead and take some negative numbers approaching 0. So it looks as though as x is approaching 0 from the left-hand side, that sine of x over x function is approaching an output of 1. So that's what I would say the left-hand limit is. it looks as though the left-hand limit of this function as x approaches 0 is going to be 1. And that's the best we can say, by the way, is that it looks as though. This is not a proof that the values approach 1. It's a series of examples that showcase that it might approach 1. Now that we've mastered that idea, left-hand limits, obviously there should probably be a right-hand limit as well. And there is, same exact definition, except that x is approaching a from the right-hand side, or what we would say from above. And that's what we use the plus sign for. So in this case, x takes on values that are slightly greater than a. So, and again, the meaning is that we can take the values of our function arbitrarily close to L by taking x sufficiently close to a as long as x is greater than a. And as I've been saying, the left and right hand limits are also known as one-sided limits. Now, if you recall, before we did a couple examples, we had this one I made up. And if you now revisit this and say, well, what if we're looking at the limit as x approaches 3 from the right-hand side? Let's see what that becomes. So I will go ahead and pretend as though I'm plugging in x values that are getting closer and closer to 3, but from the right-hand side of 3, you can see where the y values are heading. They're climbing and climbing and climbing and getting to a value of 10. They'll never attain a value of 10, but they'll get very close to a value of 10. So the right-hand limit here is going to be 10. Let's go ahead and go back to that Desmos example where we built that table and now deal with the right-hand limit. What happens as x values approach 0, but from the right-hand side? Okay, we're back here in Desmos, and you can see I still kept my table from before. This time I'm just going to erase those negatives because we're doing a right side limit. This is just a good reminder that the left-hand limit as x approached 0 for sine of x over x was 1, or looked to be 1. Let's look at the right-hand limit. Now, it looks almost identical. In fact, it does look identical, right? So all I did was erase the negative numbers from the inputs, still the outputs remain the same. So this means that this function has a symmetry, a beautiful symmetry about it. In fact, that is an even function, so therefore it should be symmetric about the y-axis. But on the right-hand side, we can say our limits as x approaches 0 looks to be 1. Again, this looks to be 1. This is not a proof that it's 1, but it's a good justification if we were to say, the limit's probably 1. Now that we know the left and the right-hand side limits for sine of x over x as x is approaching 0 both tend to 1, it's time to bring in a brand new theorem. And this is probably the first time that we're actually seeing a theorem in our calculus course because it's so early on. But this is an important theorem. This will haunt us throughout calculus. So the limit of our function as x approaches a, notice I don't have from the left or from the right there. It's just the limit as x approaches a of f of x is equal to L if and only if the left and the right hand limits of our function as x approaches a also equal L. Now I want to spend a moment talking about the if and only if statement. The if and only if is a very special type of claim within mathematics. It's called a bijection. You have a couple statements, a statement about something we call P and a logic statement called Q. Like if it's raining, then it must be cloudy or something like that. The if and only if goes both ways. It is not only that P implies Q, but it also means that Q implies P. That's what the if and only if means, that you can go both directions with the statement. So the forward part of that says that if we have the limit as x approaches a of our function, if that is actually L, then it must be the case that the left and the right hand limits must also be L. On the other hand, the if and only if also says the following: if the left hand limit is equal to L and the right hand limit is equal to L, then the overall limit must also equal L. This theorem gets used quite a bit to prove that a limit doesn't exist, because you can easily prove a limit doesn't exist if the left and the right hand limits aren't the same. I'm going to actually write that down because that's a really good use of this theorem. If it's the case that the limit as x approaches a from the left of our function is equal to L, and the limit as x approaches a from the right of our function is equal to a different value m, where L and m are not the same value, then the limit as x approaches a of our function does not exist. And that is critical to understand. So that ends up being what we use quite a bit to showcase that a limit doesn't exist, is that its left and right hand limits are completely different. So when you have left and right hand limits that are not the same, then the limit of your function does not exist. Now, something I need to say about the proof of this, from really your college algebra courses forward, pretty much every theorem should have been proven in your courses, or you should have proven a lot of those theorems. However, this theorem is a little bit out of our league right now. So although we will endeavor to prove as much as possible in this course, this specific proof requires more advanced material. So we're not going to prove this one, but we can actually use that theorem to say something about this limit right here. We already know from our investigations using the numerical, like tables of values, we've already known that the limit as x goes to 0 from the left is equal to 1 for this function. So let me write that down. And we also know that the limit as x approaches 0 from the right of this very same function is also equal to 1. By that previous theorem, if the left and the right hand limits are the same and they're 1, then this limit must be 1. I call this the overall limit because it's the combination of left and right hand limits. So the overall limit must be 1 because the left and the right hand limits are both 1. If one of those was different, let's just pretend the left hand limit was 11. It's not going to be, let's just pretend. Then that limit, overall limit, this guy right here, would not exist. Now, using that information, let's go ahead and now investigate limits graphically again to kind of pull together this and previous concepts.
Now that we have a little more limit technology under our belt, we can now look at stuff like this up here. If I were to ask what's the limit as x is approaching -2 from the left, you would then take a look at these x values as x approaches -2 from the left-hand side. In fact, you'd look at the y values and you'd say, oh, from the left-hand side, it looks like the y values are approaching maybe about a 2 actually from the left-hand side. So it looks like the one-sided limit as x approaches -2 from the left is going to be 2. The one-sided limit as x approaches -2 from the right is going to be, this looks to be about 3. By the way, the function value at -2 is actually 3. So again, the left-hand limit as x approaches -2 is going to be 2. The right-hand limit as x approaches -2 is going to be 3. Because those two limits do not match, 2 is not the same thing as 3, that means that the overall limit does not exist. However, the left-hand limit and the right-hand limit, both of those exist. You could also take a look at the one we looked at in the previous example, or the previous time we visited this page. The left-hand limit as x approaches -1 is going to be 0. The right-hand limit, again, as x approaches -1 is also going to be 0. What that means is the limit as x approaches -1 should be 0 because the left and the right hand limits match. Moving over to the right and zooming in a little bit, as x approaches 1. Well, as x approaches 1 from the left, that limit is going to be 0. The outputs tend to 0 as x approaches 1 from the left. However, as x approaches 1 from the right, it's jumping all over the place. And so because of that, that limit does not exist. So again, the limit as x approaches 1 from the left, that's going to be 0, but the limit as x approaches 1 from the right is non-existent because it's jumping all over the place, which means that the limit, the overall limit as x approaches 1 does not exist. So every limit that you're handed, you have 3 questions. Does the left-hand limit exist? Does the right-hand limit exist? And do they equal? If they do, that's the overall limit. If they don't, that overall limit does not exist. Let's go ahead and take a look at x equals 2. The left-hand limit, as x approaches 2 from the left, the outputs are approaching 0.84. As x approaches 2 from the right, the outputs approach 0.84. Those match, so therefore the limit as x approaches 2 must be a 0.84. Notice that I'm not worried about this asymptote here because that's a different conversation for a different day. And like I did in the previous video, I'd just like to round out this video with a reminder of what we have covered. There are 4 types of limits that we will learn in calculus, and we've only learned one of them, and we really haven't even learned the true definition of that limit. So just to let you know, we have dealt with finite limits at finite points, but there are other ones coming up in the future. All right, that does it for this video. I hope it was okay for you. It was pretty okay for me. And I'll see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.